Thanks for the organizers for this very nice workshop and for this opportunity to talk about this very, very recent work joint with Zhao Yang, who is a postdoc here at Illinois. In fact, we are still finalizing our introduction of our preprint, so we welcome any feedbacks or comments. So do you guys see my highlighter or pointer? Okay, good. So Stokes, in his 1847 paper, laid out a groundwork for periodic waves that travel at a constant velocity without change of shape at the free surface of a two-dimensional infinitely deep and irrotational flow of water. The motion is acted on by gravity, and in this talk, I neglect the effects of surface tension. Among many things he did, he wrote down first terms in the power series expansion of the solution when the amplitude is small, the technique now known as the Stokes expansion. He even sketched what his solution must look like, and this is his original sketch. The existence matter for the Stokes waves was treated rigorously in the 20s by Nekrasov and Lebetivita in the infinite depths and by Strick in the finite depths, all for small amplitude. Large amplitude theory began in the early 60s by Krasovsky and many others. Now this subject is in full swing. We heard some talks and we'll hear more about some of the recent advances in this direction this week during the workshop. To quote this famous paper by Benjamin-Feir, 67, therefore, there's no doubt that Stokes waves are theoretically possible as states of perfect dynamic equilibrium. But in the mid-60s, Benjamin had the difficulty creating these waves in a laboratory setting, and here is his experiment. So he had a long wave tank, and with the wave maker on one end, which would produce a periodic wave train, what you see on the left. After this wave train has traveled a long distance, therefore a long time, and over the course there were some natural disturbances. Benjamin found what you see on the right, and he thought that Stokes waves, while they exist as the solution to a mathematical equation, they might be unstable. Shortly afterwards, Benjamin offered a theoretical explanation of his experimental finding, and about the same time, Witham, based on a complete different technique, reached the same conclusion. And the conclusion is that a Stokes wave of small amplitude, and by the way, this talk is exclusively about the small amplitude. So a Stokes wave of even small amplitude is unstable in sufficiently deep water. And what I mean by that is the wave number of the unperturbed Stokes wave times the unperturbed fluid depth. This dimensionless quantity that either measures the shortness of the wave or the deepness of water. This quantity is greater than a critical value, which is approximately 1.36. The phenomenon now goes by the name of the Benjamin-Feir instability in the water wave context, or more generally, modulational instability. Similar results arrived about the same time, but completely independently, as you notice that this is during the Cold War. By researchers from all over the world, like Lighthill, Zakharov, Ostrovsky, Benjamin-Feir, many others. Later, Zakharov and Ostrovsky wrote an article about the early history of this modulation instability from their first-hand experience. And the quote, the idea was emerging when the time was indeed ripe. Fast forward 3 decades, Bridges and Milka, in their 95 paper, they proved rigorously spectral instability of a Stokes wave subject to this condition, this instability condition. And I have to say that these original arguments in the 60s by Benjamin, Woodham, and many others, while they seem to correctly predict the physical phenomenon, it is very difficult to take these arguments as they are and put them in a functional analytic setting for a rigorous proof. So this spectral analysis of Bridges and Milka is a way to justify rigorously these former arguments in the 60s. Okay. But there are some important open problems. And number one, the proof of Bridges and Milka, it breaks down in the infinite depths. Although there is a formal analysis by Benjamin-Feir that predicts that all solutions in the infinitely deep water are unstable. The reason for this breakdown of a proof, roughly speaking, is because the linearized operator for the Stokes steady wave problem, that's a part of this spectral problem that is not compact. Very recently, in fact, the archive preprint was posted in July. Nguyen and Strauss, they found a way to circumvent this difficulty and proved the Benjamin-Feir instability in the infinite depths. And I posted a preprint about a month ago that for a different proof for the same result. So this number one item is no longer open, although there are still things to do. Next, modulation instability, generally speaking, is about how modulated periodic waves would vary over a very long space and time scale. Translating that into a spectral analysis language, it's all about what's happening near the origin of the spectral plane. The proof of Bridges and Milka, it is targeted at the origin and it provides no information about what the spectrum looks like away from the origin. And this talk is focused on this issue. Last but not least, can we promote spectral instability to non-linear instability, or is there a non-linear stabilizing mechanism? This item number 3 is of course very hard, but there is some recent progress in this direction by Jiu Lin and his collaborators, although this work is still for simplified model equations and not for the full water wave problem. Again, so today's talk is about item number 2, and let's get into some more details. The numerical studies of the 4 spectrum, not just confined at near the origin, but the 4 spectrum for the Stokes waves began, as far as I can track down, in the late 70s by Longe-Higgins. But it seems McLean and his collaborators in the 80s, they are the first who demonstrated the spectral instabilities away from the origin and some facts about the spectrum of this problem. So the spectrum is symmetric. My drawing is really bad on this iPad. Symmetric with respect to the real and imaginary axis in the complex plane. And so that the spectral stability means that the spectrum is completely confined in the imaginary axis. And any unstable spectrum must be accompanied by its symmetric reflections. The water wave problem is Hamiltonian, and it is in general true for a Hamiltonian system with four-fold symmetries that a necessary condition for spectral instability is that the 2 eigenvalues collide along the imaginary axis with the opposite Crane signature, which Bernard discussed yesterday, so I'm going to skip the detail. Now, for the water wave problem, for amplitude, say epsilon, is 0, that means the trivial solution. And the trivial solution means zero, no wave and no flow motion. Such a trivial solution is, as you expect, is stable, and its spectrum is it wraps around the imaginary axis. Now, a little more calculation will tell you that there are countably many collisions of eigenvalues. They are all very separate to each other along the imaginary axis. And these eigenvalues are special in the sense that they are associated with two Floquet exponents, and the Floquet exponents measures, roughly speaking, the quasi-periodicity of the perturbation. So there are two Floquet exponents, one k and the other k prime, and their difference is an integer multiple of a wave number of the unperturbed Stokes wave, so that the corresponding eigenfunctions, they will live in the same quotient space of periodic functions. The McLean and his collaborators in the 80s, their numerical investigations suggest that now each and every of these resonant collision eigenvalue, they will lead to spectral instability for some non-zero amplitude. Now, what was mildly frustrating to us was most of these numerical investigations in the 80s and later, when they present their numerical findings, they focus on how the spectrum depends on various parameters and various circumstances, and they do not explicitly show what the spectrum looks like, except one work. This DeConnick and Oliveira 2009 paper. So in this slide and the next slide, I'm going to make my own very biased summary or highlight of this paper, where a lot of other things are going on. And the choice I made here agrees with what Bernard chose to discuss yesterday in his talk, some sanity check. So these plots are happening in the complex plane, and they represent the spectrum for the Stokes wave problem. Now, in their setup, the wave number of the Stokes wave is set to be 1. So their H is the dimensionless deepness parameter. So that's the same as the quantity that Benjamin and Woodham used for their arguments. So when H is 1.5, then the underlying Stokes wave is subject to the Benjamin-Feir instability. This value is bigger than this critical number, 1.3 something. And that manifests as this unstable spectrum that comes off from the origin. And this upper right corner is the blow up picture of the spectrum near the origin. This is not new to us. In fact, this is exactly what the Bridges and the Milker prove. But the numerics shows some extra unstable spectrum that comes off away from the origin, and the location here where this unstable spectrum bone is exactly at this resonance collision, the closest to the origin. And if you blow up, then you see a bubble of instability. Now, you can find more unstable spectrum as you run off from the origin along the imaginary axis. But what seems, it seems that in this situation, the modulation instability around the origin is a dominating one, right? Because the larger the real part is, larger the growth rate. So that these extra unstable spectrum, they may provide extra spectral information, but probably they will not alter the wave dynamics to the core. On the other hand, now, if when H is now 0.5, then the underlying Stokes wave is no longer subject to the Benjamin-Feir instability. And in fact, there is no unstable spectrum coming out around the origin, right? However, numerics shows a bunch of unstable spectrum, and it is born from this resonant collision of eigenvalues. And when you blow up, you see a bubble of instability. So the conclusion here is the Stokes wave behind this spectral picture, it is not Benjamin-Feir unstable, but it is spectrally unstable nonetheless. And these numerics teaches us that there are more unstable Stokes waves than what the Benjamin-Feir instability predicts. This has been a completely open problem analytically. Not only there has been no rigorous proof for this kind of instability, but also there has been not even a formal asymptotic analysis was analogous to what Benjamin and Witham did for modulation instability. So what I want to do today is to present a theorem and hopefully proof of this high frequency instability. This name high frequency instability is due to Bernard, and the idea behind it is when this instability happens, then an unstable solution to the linearized problem will take the form e to the lambda t times some function of spatial variables. And here lambda is an unstable eigenvalue, so it has a non-zero near part. And this instability is happening away from the origin. So the imaginary part is not so small. In such a case, the solution is exponentially growing while rotating in time. And this behavior is completely different from modulation instability, where this lambda is near the origin. Okay, so this is what we're after. Now, before I get into technical details, by the way, the proof is extremely technical. I want to say, I want to discuss some of the main ideas of the proof. So say that the linearized operator, abstractly, the linearized operator for our spectral problem is Kelly L. It has at least two independent parameters. Epsilon is for the amplitude, and the K is the flow K parameter. Now, what Bridges and Milke did is they first drop the flow K. Then, now you're dealing with co-periodic, the same period perturbations as the underlying wave. And then we try to compute the spectrum of that operator at the origin explicitly. And this is possible because the water wave problem is Hamiltonian. It turns out that there are 4 eigenvalues at the origin with a Jordan chain of length 2. We can also calculate explicitly the corresponding eigenfunctions and list for small amplitude using the Stokes expansion. So in other words, we completely characterize the spectrum at the origin when K is 0. And then we turn on K, the flow K, and then we watch out how these 4 eigenvalues move around. This approach was not very helpful for our purpose, unfortunately, because this explicit spectral information for non-zero amplitude, this is available only at the special location of the origin, and this information gets lost once we depart the origin, while we try to say something about away from the origin. So we turn this idea upside down, and our strategy is that first we drop the amplitude parameter, and then we are looking at the linearized operator about a trivial solution. And this operator has only constant coefficient, so that we can completely characterize the full spectrum in the everywhere in the spectral plane. And it turns out that there are two branches of spectral curves that covers the imaginary axis. And then we turn on the amplitude parameter and we watch out how these spectral curves will deform with epsilon. And this was the idea that I exercised for this alternative proof for the Benjamin-Feir instability in the infinite depths. Another thing that I want to comment, the water-wave problem, as we all know, is a free boundary problem. So step 0, before we do any of these, we have to fix the free boundary. Now, in an irrotational flow, which we are in, it is traditional, almost traditional, to reformulate the 2D water-wave problem in 1D, into 1D problem by introducing some non-local operator, like a Dirichlet-Neumann or like a Hilbert transform, something like that. And this was convenient to get around the difficulty of non-compactness in the infinite depths. And this was one of the reasons that I worked to develop spectral analysis for non-local operators in my past life. Now I'm abandoning this idea. And now in this work, in the follow-up works, I'm formulating the 2D water-wave problem into another 2D domain, but with fixed boundaries, so that I will not see any fancy non-local operator in my reformulation. And I'm exclusively working on PDEs and ODEs, no non-local operators. The reason is the spectral analysis for non-local operators, the accounts are often not detailed enough, not as powerful as ODE theory, so that I cannot see everything that I want to see. On the other hand, there is a widely successful work of stability theory for PDEs. So what I'm doing here is I want to bring the water-wave problem and put that into this big word of stability theory for PDEs. And I want to use the strongest tools in that word to hammer this problem down. Specifically, my end result is periodic Evans function. This is the determinant of some matrix, n by n matrix. And for the Stokes wave problem, it is either 4x4 matrices or like a 2x2 matrix. Of course, this matrix contains all the spectral information, so it's not the easiest kind of matrix to deal with. But anyways, it's a 4x4 matrix you deal with. And this determinant function is analytic in epsilon and k, and also lambda, the spectrum, the spectral parameter. And when there is a root to this determinant function, then that lambda value that gives the root of this determinant function, the period Evans function, will be the spectrum of the original problem. Now, I will go ahead and present the main results. And then if I still have time, then I will discuss some other technical aspects of the proof. But let's make sure that I keep the punchline. So as a test drive, we revisited the Benjamin-Feir instability, and we reproduced the result of Bridges and Mikyoung. In our setup, the water depth is set to be 1. So the wave number kappa plays the role of this shortness of the wave, and that's the same as h that appeared in the Bernard's and Katie's work, and it's the same as this kh that appears in the Benjamin and Widham's work. So we should see that here we have this critical parameter value that's the same as everyone else. Not only this value agrees with everyone else, our index formula, index function, is the same as the index function of bridges and Milke, up to some factor of strictly positive function. And this expression also, this function also appears in the work of Benjamin and Witham. So again, Benjamin and Witham were right, but more importantly, our technology works. But there is some bonus. Now, what we do and what everybody else does is asymptotic analysis. So we try to write out the spectrum as the powers of small parameters. And in this game, there are two small parameters, the amplitude epsilon and the flow K parameter K. And in order to draw our conclusion, we needed the coefficients of K, K squared, and epsilon K. And now the Bridges and Milke paper is not the easiest kind to read. So it's a slightly, I don't understand 100%, not yet, but it looks like that Bridges and Milke, they never needed to compute the K squared term. But anyways, now we have this extra information so that we can update the spectral picture of this problem. And now these plots that you see here, these are the spectrum that we plot in the complex plane, and they are exact. We choose some kappa that is unstable, and then we evaluate our coefficients of these expansions at that kappa to produce these curves. This is for one value, but this is a genetic picture. As we move kappa, these curves, they qualitatively stay the same. So this is this is a genetic picture of the Benjamin-Feir instability. And we see that there are two distinct branches of the curves that comes out from the origin in the first quadrangle, and then the rest of the quadrangles are filled by symmetry. Now, there are two branches because there were two spectral curves when epsilon is the amplitude 0, which has the opposite curvature at the origin. So we are expected to see two distinct branches. We expect that each branch will make a closed loop. So the solid one will make a figure 8, while this dashed one will make a figure infinity. This figure 8 has been reported by in numerical works, for example, in Bernard and Katie's work. But as far as I know, this figure infinity has not appeared on this scene, not yet. Well, we can also calculate, we can exactly calculate what these curves at the outset looks like. And it turns out that this figure infinity curve, figure infinity is much smaller. It's like an order of magnitude smaller than figure 8 curve. And we think that this is maybe why numerical computation cannot resolve this. This is too tiny to resolve. But anyway, so an updated Benjamin-Feir instability picture. So when Benjamin-Feir instability happens, then there are two sets of closed loop on the spectral plane. One figure 8, and this is the dominating one, and then one tiny figure infinity. But anyways, this is not the entirely new result. This was just a test run. The main result of our work is the high frequency instability. And now remember that there were countably many collisions of eigenvalues along the imaginary axis. And so the closest one from the origin, where two flow K parameters are differed by twice of the wave number. Under that situation, around this eigenvalue, we find we have spectral instability if a kappa is in this interval, bounded interval. the lower bound is approximately 0.63, and upper bound is slightly greater than 1. And this range is, this joint is outside of the Benjamin-Feir regime, which takes off at 1.36. And our analysis does not detect any instability at other collisions, and list up to the order of epsilon squared. We also examine non-colliding, non-resonant collisions. So we examine everywhere along the imagined axis, and we do not find any instability up to this order. So the only instability, our analysis, when we sweep along the imagined axis, is at the origin and then the next collision. So good news is that we have proof of this new unstable waves other than the Benjamin-Feir unstable waves. But bad news, maybe not. Our results do not, that our numbers not agree with the numerics. Now, if you go back to the DeConnick and Oliveira's paper, then now their H is the same as our kappa. So when their H is 0.5, this is outside of this interval of unstable wave number from our theorem. And yet they find this unstable spectrum. And moreover, they find the unstable spectrums further away from the origin. I don't think there's nothing wrong about with this numerical computation. I think actually we are both right. We think the reason for this disagreement is the question, how small is small? So our analysis is as the amplitude goes to 0, this is a limit, our analysis is done, and the limit as the absolute goes to 0. So it's infinitesimally small, arbitrarily small amplitude. That's our analysis about. And when you do numerical computations, you assign some smallish value for your amplitude. For example, Bernard and Katie, they choose the amplitude parameter to be 0.01. And it's not clear how small is that. So there is so infinitesimal, the limiting analysis and the small but finite amplitude, that they are not the same. And if we think that if we were to, with our current technology, we cannot, but if we were to make a proof for small but finite amplitude, and then if we can study how these things changes with amplitude, then maybe, hopefully, we can cover these numerical results. And there are some supporting idea in this famous paper of McKay and Stockman, but in the interest of time, I may come back to this later if I have time. Now, the last thing that I want to discuss is the level of technicality of the proof. I don't think I have time to go over this proof. So let me say how much work you have to do to prove this theorem. So for the Benjamin-Feir instability, again, so our work, it goes to compute this 4x4 matrix, so which it goes to one part, we compute this determinant. And this matrix, so we compute in the asymptotic sense. So we expand in the powers of small parameters. And we need actually at least 7 of them. So this is just a cut. And each entry of this matrix solves an inhomogeneous boundary value problem for an inhomogeneous, let me rewind that. Each of this entry comes from a solution to a boundary value problem of inhomogeneous Laplace equation. Okay, and the hardest part is to compute this forcing term, the inhomogeneous term. For the Benjamin-Feir instability, it is manageable, and that's why I displayed the index function explicitly in my theorem slides. Now, but for the high frequency instability, this is truly daunting, and this is a page from our preprint, and you don't have to read. Now, you need two of these pages. So there are a bunch of coefficients, and they are already written in a shortening notation. So we need about 2.5 pages of these coefficients. We add them up, and that makes one coefficient of one of the terms in our inhomogeneous term. And at this order, the inhomogeneous term is made up of 12 functions. So we need 12 of these guys. That's just the inhomogeneous term. And then, so we solve that. And we need to solve, I don't know, like hundreds of them. I'm not exaggerating. So clearly, this is not a human job. And luckily, Zhao is a MATLAB genius. So we set up this symbolic calculation, and we do it. But even with the help of MATLAB, we have to do a lot of hand calculations. Now, so this one term in the inhomogeneous term takes about 2.5 pages to display, and it takes about 5 kilobytes to save the MATLAB data. And now for this high frequency instability, the one term, one entry in this matrix, by the way, it's a 2x2 matrix. So it's supposed to be simple, but this matrix entry, it takes about more than 500 kilobytes just to save this MATLAB data. So it is impossible to display this on paper. So that's why we do not display this index formula in our theorem. But just to say that one of the essential ingredients in this proof is Zhao's hard work, which I cannot underestimate. I think I don't have time for any major items, so let me stop here and I'll take any questions if there is. Thank you.
Thank you very much for your talk. So is there any questions or comments?
Yes, I have a question. Vera, hi.
Yeah, hi.
Yeah. We had quite a lot of difficulty, not only with the 4x4 matrices, but for Benjamin-Feir case, but also for reducing just the reduction of the infinite dimensional part to the 4x4 to a finite dimensional problem where we used basically Lyapunov-Schmidt. And you haven't mentioned that at all. I wonder.
Right. So we also, okay, thanks for the question. So that's one of the steps in our proof. And yeah, I just thought that since I cannot go through the whole steps, so I just skipped all the steps altogether. We do make reductions into the finite dimensions. But as I said, that one major difference between what we do and what other people do is so our principal part. So the finite dimensional part for us is much simpler than what you do, because you're this finite dimensional part. The part that you get to project, it depends on epsilon, if I understand correctly. But we're only taking the constant coefficient, the principal part. Okay, so this part is super explicit and super nice. But then we have to pay price later, right? We're done for all the things on B, and that's why our the inhomogeneous terms are enormous and hideous looking. I don't know if that answers your question.
Yeah, I thought in your matrix you still had epsilon. In your 4x4 matrix, you still had epsilon as well as delta in there.
But
so it wasn't just the L part; it was also the B part.
Sure. So that, yes, it's all combined. This Evans function is a whole melting pot. So we're solving for this finite dimensional part, but this is a slave to this like a range part, right? That has all the difficulties.
Okay.
So that when we solve this problem, so because the original problems in the infinite dimensional and it has lots of complications, so that if after we deduce, well, it's like now the 4x4 matrix, but if you look into, look carefully, what's going on in that 4x4 matrix, lots of complicated things going on. And so that the solution in this finite dimension, so the part of the solution in the finite dimension, it contains all the parameters. And this matrix A is a fundamental solution to, so we can write this in this abstract as a matrix equation, and this A is nothing but a fundamental solution of that matrix equation.
Yeah.
Yeah. Yeah, so you cannot avoid the difficulties. There's no golden way in this problem. You just have to get your hand dirty. I think that's the lesson that we learn.
Thanks, Vera.
Thank you.
Is there any other questions?
Thank you, Vera. Just to make sure, thank you very much for a nice talk. Just to make sure that I understand the logic of the proof. So you mentioned that you first fix the amplitude to be 0 and consider the whole spectrum when you vary the parameter, and then you start to perturb the amplitude, right?
Right.
But is that also but it seemed to me that the order of the parameters is the other way around in the main theorem. Do you prove that for sufficiently small Stokes wave, then for all more enough lucky number, you have the instability, because that is how we state our theorem. Is that also the same order for you in your theorem?
So this part I have not looked into very carefully. And the way that we arrange these parameters are different from what other people do, right? Because again, this periodic Evans function is a big melting pot. So we put everything in this Evans function. Come on, then so that so this determinant depends on the lambda. Okay, so we do not isolate lambda. We don't have to. And then they get the blockade parameter and the epsilon. So it depends on all, but it depends on all these arguments analytically, so that we can write down it's a multivariable power series. And it turns out that the lowest term of this Evans function is a fourth order in lambda. So we just, and these terms, well, not this is cut. So the order up to this order, these powers, are the orders that we need to get to the conclusion.
Right.
Right. Yeah, I think it's okay. So we now we make expansion, and then we want to solve this equals 0, but for lambda, which is a function of flow k and amplitude. Okay, and here you have to do some work to get to this ansatz.
Right. So the question is right there when you
exactly, yes. Yeah. So here we have to use other things to get here, and it's basically like a matching, like a powers, matching like a powers. So like first you can just assume that, first of all, so the one difficulty that I asked you actually by email is that this lambda expansion, it doesn't have to be analytic, right? Yeah. So that there's no a priori like ansatz that we could use. And here we just make a guess, and we are lucky to that this works. But now I think we have a more systematic way to handle this. So that's what we're working on. But at this point, this is somehow like based on like our a priori knowledge of what's going on. Yeah, so this part is not trivial, and yes, it requires some thinking.
So but like your guess is the order is the same, right? I guess once you fix a sufficiently small amplitude, then for more Blocker number, you should get instability. Do you still think that's the case for your proof? Or you think you can choose the two parameters more independently? I'm not sure you understand.
Oh, no, I understand the question. Okay, so they are in the beginning. Okay, so we don't have, let me think this way. Let me say this way. So we do not see instability. So, okay, so short answer is epsilon cannot be too small. It's small, but cannot be too small, depending on what your flow K is.
I'm sorry. I think I've been talking about the Benjamin-Feir, right? Is that?
Yes, this is Benjamin-Feir instability.
Oh, you say absolutely.
Yeah, this is the answer is different for high frequency instability. So for Benjamin-Feir instability, both epsilon and both amplitude and flow K are small, but so we fix the theorem will work if we fix small flow K and choose the amplitude small accordingly.
Oh, so that would be a reverse order compared to, yeah. Okay, that's interesting. Maybe we can talk more about that later. Just a quick question. You mentioned far up in the imaginary on the imaginary axis that you don't get instability up to the order of epsilon squared.
Epsilon squared, yes, because this is asymptotic analysis.
Right.
Yes.
So the method would allow you to continue if you're willing to do more computations or like.
Yes, but I don't think this is a way to prove a spectral stability, because then you have to calculate all possible orders, and how can you do it? If you're extremely lucky, there may be some recursion relation, but our coefficient is so hideous, and we not try to simplify it, but we don't think there is any useful recursion relation. So that of course this so like if we don't find these instabilities, then the other guys are stable or not. That this is an important question, and I think for that question we directly study this determinant. I think that's what we are working on currently.
But you expect it should be stable up there?
Yes, because if you look at what's going on in the proof, this instability is happening when there's Jordan block, right? And so that, and we can see like when like the entries become zero, that we have some idea. So that when it's not happening, when there's no Jordan block at the order epsilon square, then we think that there is a very like a slim chance that there will appear suddenly Jordan blocks in a higher order, because higher order the coefficients at higher order, they are built upon like the coefficients in lower order, right? So that it is very unlikely, although this is not a proof.
Thank you very much. Okay, I'm looking forward to discussing more with you. Thanks.
Sure.
Thank you very much. Is there any other question?
Yeah, can I ask a question?
Yes.
Yes.
Very nice talk. About your Benjamin-Feir result, you have the figure eights, or you know, the part of the figure eight at the origin. You have the part of what you call the figure infinity at the origin. Are they tangent to each other?
Yes, because so they are at the order of k, they are the same, and then the coefficient of order k square, they are different.
So yes, that's the argument why Bridges and Milka didn't find it, because they didn't go to k squared?
That's what I think. Yes.
Okay. All right, thank you.
Thank you.
Thank you very much again for your talk.